How can a single truck generate a suction force so powerful it can lift water, mud, sand, and even solid objects from pipes buried several feet underground? Most people see one of these vehicles working on a street and think it's just a simple tanker truck, but nothing could be further from the truth. What's inside is a masterpiece of industrial engineering capable of creating an extreme vacuum and blasting water at pressures high enough to break through years of buildup. But before we reveal all the secrets of these extraordinary machines, if you're fascinated by heavy engineering and want to understand how the vehicles that keep our cities running work, subscribe to the channel now and like this video, because we're going to look inside one of these trucks. Now let's get started. Inside the truck, two technologies work together to make it an almost unbeatable tool: a suction system that vacuums material from underground and a jetting system that launches ultra-high pressure water to break through clogs, dislodge sediment, and wash away debris. Combining these two systems allows for cleaning sewer mains, clearing entire networks, and restoring flow to invisible but absolutely essential infrastructure. Inside, processes occur that most people are completely unaware of. High-speed turbines, internal pressure drops capable of moving hundreds of pounds of sediment, hoses designed for extreme conditions, and separation mechanisms that store the extracted waste. Everything is synchronized within a single vehicle. The power of vacuum, what actually happens inside the truck to create that massive suction power, allowing it to pull water, mud, and debris from the depths of the sewer system. Inside the system, there isn't a force pulling the material in the way many imagine. Everything starts when the equipment displaces massive volumes of air, completely altering the pressure balance inside the tank. As that air is pushed out, the inside of the tank becomes a low-pressure zone. That's when atmospheric pressure pushes the sludge, water, and debris through the hose and into the tank. Under these conditions, vacuum doesn't mean a total absence of air, but rather a pressure drop intense enough to maintain a continuous flow from underground to the tank. The pump draws air from the main tank, the suction valve opens, and ambient pressure does the rest, moving even heavy materials without relying on direct mechanical force, but rather on the pressure difference between 2 points. This vacuum is generated by 3 main types of industrial pumps. The most common are rotary lobe pumps, consisting of 2 rotors that spin in sync within a sealed housing. Since they don't touch, they can move air without excessive wear and provide a very high flow rate, ideal for handling dense sludge. Other systems use liquid ring pumps, where a rotor spins inside a chamber partially filled with water, creating low-pressure cavities that displace air. This is an especially stable setup that also handles fine particles well. There are also units that use vacuum turbines capable of moving large volumes of air at very high speeds, which are particularly useful for lighter cleaning jobs. Once the vacuum is established, the suction process enters a continuous phase. Ambient air pushes the content into the hose, and the flow carries sewage, sludge, sand, grease, small branches, and other materials blocking the pipes. All of this content enters the truck's tank at high speeds. The tank is built with heavy-duty steel to withstand both the internal pressure drop and the impact of solids. Once inside, the flow leaves the suction zone and enters an environment where various mechanisms work to protect the pump. The heaviest solids lose speed inside the tank and drop to the bottom thanks to cyclonic separators. While the air continues toward the pump, protective filters prevent fine particles from entering the vacuum lines, and safety valves limit the maximum vacuum to prevent structural deformation or collapse. However, as effective as vacuuming is on its own, it has a limit, and it cannot move a blockage that has become completely solid or compacted over years. Hardened grease, sediment, packed sand, and even roots can resist the suction flow. At this point, extraction isn't enough, and the system needs something more than just a vacuum: the jetting system. This is where ultra-high pressure water jetting comes in, capable of firing a stream so concentrated and powerful that it breaks through compacted sediment, hardened grease, and even small roots blocking the pipe. Jetting relies on an industrial pump capable of compressing water with enormous force, far beyond what a residential pressure washer can generate. The pressure can exceed 2,200 to 3,000 pounds per square inch. That's enough to cut through hardened grease, dislodge compacted sediment, and clear a path where the vacuum can no longer advance. This pump is usually driven by the truck's PTO, or power takeoff, continuously transmitting a massive amount of mechanical energy. Unlike a consumer-grade machine, the pressure here must remain stable over long working periods. That's why it requires a robust structure, high-strength pistons, and lubrication systems designed to operate without excessive wear. With the system running, clean water from the truck's tank enters the piston pump, often a triplex pump, where it is compressed with immense force. Upon exiting, the water is directed toward the high-pressure hose. This hose ends in a specially designed nozzle, built not only to blast the jet forward, but also to direct part of the flow backward. This configuration allows the nozzle to propel itself forward through the pipe, while it pierces or strips away material stuck to the walls. For everything to work without interruption, the jetting system must use clean water. Any particle could damage the pump or disrupt the jet's shape. This is why the trucks carry large amounts of water in dedicated tanks. When that steady jet hits the inside of the pipe, its effect changes depending on the type of blockage. Against hardened grease, it acts like a liquid knife, slicing the material into small sheets. When hitting compacted sediment, it penetrates between particles until it breaks down their internal structure, turning them into fluid mud. In accumulated sand or gravel, the hydraulic movement lifts and clears them without needing direct mechanical force. Meanwhile, for small roots, the nozzle works almost like a micro-tool, fragmenting them without damaging the pipe. This entire process is continuously coordinated with the vacuum system. The jetting breaks, dislodges, and mobilizes the material, while the vacuum captures and transports it into the tank. If the order were reversed, the debris would just settle further down the pipe. That's why the work is performed from the furthest point back toward the manhole, ensuring everything dislodged moves toward the truck. The sludge tank. Once the pressurized water breaks the clog and mobilizes pounds of sediment, all that material ends up in the large sludge tank, the centerpiece of the truck. Far from being a simple cistern, it's an industrial structure designed to withstand extreme stress, internal impacts, pressure changes, and the aggressive composition of the waste. In many models, capacity can reach nearly 2,600 gallons. The tank is constructed of thick steel with reinforced welds and a completely hermetic design. It must withstand both the vacuum generated during suction and the stresses caused by the entry of sludge, rocks, and sand. Additionally, its seal prevents the emission of gases, odors, or vapors from the interior, a fundamental requirement for operating in urban areas. Inside that structure, when the mixture of water, mud, and waste enters the tank, the flow slows down. This sudden drop in energy is key to allowing the heaviest solids to fall to the bottom of the tank by gravity. This dynamic is reinforced by internal systems designed to improve separation. Among these mechanisms, cyclonic separators generate a spinning motion that helps separate solid particles from the air and liquid. And there are also internal baffles, metal plates strategically placed to slow down and divert the flow. Meanwhile, water traps catch foam or bubbles, and safety filters prevent fine particles or corrosive vapors from reaching the vacuum pump. As the tank fills, this internal balance requires constant level monitoring. Some trucks feature sight glasses, while others use sensors to alert the operator when capacity is nearing the limit. Exceeding it is not only dangerous but also violates waste transport regulations. When the tank reaches its operating capacity, it's time to empty it. There are two main methods: rear tipping, where the entire tank tilts to discharge the contents into a hopper or authorized facility, and positive pressure emptying, which involves reversing the vacuum system to push the contents out. In both cases, disposal can only be done at authorized sites, typically treatment plants. Specialized hoses. To fill that tank, the vehicle needs delivery systems capable of withstanding vacuum, pressure, and extreme abrasion. From the outside, you only see a flexible tube, but in operation, the hoses become a direct extension of the truck. There are two main types. The first is the large diameter suction hose, responsible for transporting the sludge, sewage, sand, leaves, and root fragments that the vacuum pulls from underground. To withstand the extreme vacuum generated inside the system, it's made of heavy-duty rubber, reinforced with an internal metal spiral that prevents it from collapsing. Its diameter usually ranges from 4 to 6 inches. The second is the high-pressure hose, which is much thinner and more flexible. And its job is to deliver clean water at pressures exceeding 2,200 to 3,000 pounds per square inch. For this reason, it's composed of several layers of synthetic rubber and textile or metallic reinforcements. Given the weight and forces involved, handling them requires specific mechanical systems. The jetting hose is usually wound on a hydraulic reel that can extend and retract it continuously, accompanied by guide rollers to prevent twisting. In the case of the much heavier suction hose, it is handled using articulated arms or booms mounted on the rear of the truck. Inside the pipe, the jetting hose behaves in a very specific way. The nozzle projects part of the jet backward, creating a self-propelling effect that makes the hose move forward on its own through the conduit. In this way, it can travel many feet underground without direct manual intervention. And the operator simply regulates the advance and retraction from a side panel on the truck. The suction hose is placed where the dislodged waste accumulates and remains fixed, allowing the vacuum to capture all the material. Both hoses are controlled via side panels, equipped with pressure gauges, vacuum gauges, quick-close valves, and drive controls. These systems allow for precise regulation of water pressure, vacuum levels, and hose positioning. Coordination between the two hoses is essential. The jetting breaks and strips the blockage while the suction collects the dislodged material and transports it into the tank. This synchronized effort prevents the waste from resettling. Critical safety systems. Precisely because the entire system operates with extreme vacuum and ultra-high pressure water, the truck incorporates a strict set of safety systems capable of managing gases, pressures, and environmental conditions. The first major risk comes from the vacuum. The pressure drop inside the tank can cause a hose not designed for it to collapse, or even deform the tank itself if the structural limit is exceeded. This is why the truck uses vacuum gauges to show real-time internal pressure, along with relief valves that open automatically when the vacuum exceeds the safe range. The second major risk comes from water pressure. The jetting system works at pressure levels high enough to pierce a fragile pipe or cause violent hose kickbacks if the nozzle becomes blocked. To prevent this, the trucks include adjustable pressure regulators, hydraulic relief valves, and high-precision gauges to monitor even the smallest variations. And the third major risk comes from underground gases. Inside sewers, flammable gases like methane, toxic gases like hydrogen sulfide, and even oxygen-deficient atmospheres can accumulate, leading to asphyxiation. This is why, before opening a cover or starting any work, portable detectors are used to check air quality and detect dangerous concentrations. If levels aren't safe, the area must be ventilated. The fourth risk comes from the waste itself. The sludge stored in the tank can contain sand that acts as an abrasive, corrosive chemical residues, or materials that generate gases during storage. For this reason, the tank is built with thick steel and equipped with internal traps that prevent vapors or foam from reaching critical areas of the vacuum system. Why this design is the global standard. At first glance, it might seem like there are many different ways to clean a sewer network. But when pipes are deep, narrow, or deteriorating, most solutions are no longer viable. Underground infrastructure changes in diameter, material, and age within just a few feet. This requires a system capable of adapting without losing effectiveness. That's why this design eventually became the global standard. It wasn't the result of a single isolated innovation, but rather a direct consequence of how its systems interact in real-world conditions. It combines the necessary power to intervene with the control required to avoid damaging the network, all in one vehicle. The vacuum and jetting system dominates for one clear reason. It doesn't just break the clog, it removes it completely, preventing the dislodged waste from recompacting elsewhere in the line. Ultra-high-pressure water jetting breaks down hardened grease, compacted sand, dense sludge, and small roots. Meanwhile, the vacuum immediately captures all that material and transports it to the truck's tank. No other method offers this coordinated double action. Simple pumps can't break through tough obstructions, and purely mechanical methods require direct access and lose effectiveness at great depths. Before this design became universal, cities relied on much slower and more dangerous procedures, involving frequent manual entry into manholes and rudimentary tools. It wasn't uncommon for incomplete cleaning to cause new blockages just a few feet away. The arrival of the vacuum and jetting truck didn't just improve efficiency. It permanently replaced obsolete methods that required more personnel, more time, and a much higher level of risk. Its standardization isn't just due to technical capability, but also operational advantages. This type of truck can work at great depths without the need to excavate or dig new trenches. It cleans long sections of pipe from a single access point, avoiding traffic disruptions and reducing the impact on the city. Its action is fast, continuous, and controlled, allowing it to handle emergencies like local flooding or critical blockages in minutes. It handles virtually any type of waste, from mud and heavy sand to solidified grease, roots, small objects and even sediment accumulated over years. This same operational efficiency ultimately reflects in the economics. This design significantly reduces the number of workers needed for each job, cuts total operation time, and avoids costly civil works like excavations or traffic diversions. It also minimizes the risk of major network damage, reducing the likelihood of breaks caused by internal pressure or sediment buildup. In other words, a vacuum and jetting truck doesn't just clean, it prevents breakdowns that would cost much more. Thus, rather than just a niche solution, this design established itself as the global benchmark by bringing together efficiency, safety, and adaptability in a single system. It doesn't matter if you're working in a historic city with ancient pipes, in an industrial zone with heavy waste, or in a modern network with more fragile materials. The vacuum and jetting system remains the most efficient way to keep the underground infrastructure that allows a city to function operational. Conclusion. This is where the vacuum and jetting truck stops being seen as just a tool and starts being understood as a fundamental piece of the puzzle for maintaining the underground networks that allow a city to breathe, drain, and stay alive. Its ability to combine extreme vacuum, ultra-high-pressure water, and advanced separation and safety systems makes it a machine capable of solving problems that no other method could address so effectively. Throughout the video, we've seen how every part of the truck performs a critical function and how they all work together as a single machine. The jetting breaks through the toughest clogs. The vacuum carries the material to the tank. The hoses allow it to reach deep and difficult areas. And the safety systems keep pressures, gases, and the inherent risks of a complex and often aging infrastructure under control. It is this coordination that allows these machines to operate with precision and reliability in environments where there is no room for error. Behind every job, there is more than just power or technology. There are engineering decisions designed to act without breaking, to clean without invading, and to solve invisible problems without disturbing the city's surface. This balance between force and control is why this design has come to dominate such diverse networks. At their core, these trucks are one of those examples of applied engineering that is rarely seen up close, but whose impact is massive. That impact is felt in everyday life because they keep the underground networks clear, allowing a city to run without stopping. But if you want to keep exploring how the machines that sustain our city's invisible infrastructure operate and understand the engineering that makes them possible, subscribe to the channel and hit the like button. Let me know in the comments if you knew how these trucks worked, or if you've ever seen one in action. I'll see you in the next video, where we'll continue discovering the secrets of heavy engineering.